Okay, so let's look at hashing methods. Okay, so with hashing methods, what we have is that, say we might have Bob, and Bob has some data. So what we want to do is to be able to create a thumbprint of that data, so that the data that we have can be represented in some form that we can actually check the original data to see that it has been changed. So all the ones and the zeros will be put into a one-way function called a hash function, which will allow us to be able to go from the data to produce a hash. It shouldn't be possible to reverse the hash back into the data in the way that we would do with other transformations such as in encryption. We often use this in terms of verifying the data, but we might also use it in terms of creating what's called a hash signature. So if Bob uses his private key to encrypt a hash, then his public key can be used to be able to make sure that the data has been signed by him. But for just now, we'll just look at the creation of a hash. And this is normally a fixed format hash. So we have a given number of bits that will define the length of the hash. So no matter if we have 1 byte of data or a terabyte of data, we always produce the same size of hash. And we always use a standard method that everyone can actually compute. So first, let's look at the methods that we have. Okay, so one of the most basic methods is the MD5 method. Then we have what's called SHA-1, and then SHA-2 includes methods such as SHA-256 and SHA-512. Basically, they differ from their methods. So this is SHA-1, this is a SHA-2, and now we even have SHA-3. The methods that we use are actually different from each other to make sure that we improve the security each time. And probably the one that's the most, the best defined for this current era is SHA-3, which uses a new method called a sponge method, and it was standardized by NIST. And we can see that it's used in modern blockchain methods such as Ethereum, and it's well suited for lightweight cryptography and for limited processing and memory devices. But for each of these methods, we have a hash of a certain length. So this gives us a hash of 128 bits. This gives us a hash of 160 bits. And this is 256 bits. And so on. And here we have 512 bits in case we need an extremely long hash. The longer the hash, the more data that we can represent, and as we'll see, the less chance there is of a collision between the hashes. And the collision is caused when two data elements are different but produce the same hash. So the smaller it is, the weaker the hash method is. And MD5, as we'll see, doesn't take that much to be able to create what's called a hash collision. It is also possible with SHA-1 to create a collision, or theoretically possible, and it was practically shown that it's possible to create a hash collision. So when we're using hashing methods, we typically don't use these methods now, and we move on to the 256-bit methods, which should not produce a hash collision within a reasonable time for different data sets, but MD5 is certainly very weak. So the hash itself is made up and can be represented in a hex format. So if we think of hex, then we get 2 hex characters represents 1 byte of data. So for this, if we have 128 bits of data, then we get 16 bytes. 16 bytes is 32 hex characters. And then base 64, so our format might be something like 53 to A, B, F, 5. That would be our hex signature for an MD5. Obviously, if we're using 160 bit, then it will be a longer hash. And we only have to change 1 bit of our data to produce a different hash. In the other format that we use is base 64. And in base 64, we use 6 bits per base 64 character. So in this case, if we divide that by 6, then we get 22 base 64 characters. And one thing we know about base 64 is that it must be a multiple of 4 characters. So we round that up and we get 24 base 64 characters makes up an MD5 signature. And often we'll see the equal signs at the end of a base 64 hash, because the padding happens at the end to fill up the multiple of 4. Okay, so we get 32 hex characters, or 24 base 64 characters will give us our hash signature for an MD5. 1 bit of data will change the whole signature. In a good hashing method, we change 1 bit and it will change all of the output bits and ripple them, and there is an equal chance of each of the bits actually changing. Okay, so that's our hashing methods. And then an important element of this is what's called salt. The problem that we have with hashing methods is that the hash we produce is always the same for the same input data, as it should be. So our intruder could build a table of hashing values called a rainbow table. So if we have a rainbow table, we might have words and phrases and the hash. Then each of these words will be defined and we'll get a hash for each one. So then, if it's a password that's hashed, then an intruder could go through common words and look up the hash in the rainbow table. When it finds a match, then it's possible to map the word back again. So we can get massive rainbow tables, and it's fairly quick to be able to recover the hash. But that hardly ever happens, because what we have is a salting method. And with salt, we might take, say, a password of Fred, and then we'll add on a random nonce value. Let's call this random nonce Bert. So when we create the hash, we take the word and we add on our random nonce value to make a new string which can then be hashed. So this will create a new hash for us, 593A C2 and so on. Along with this, we must now store the salt value, because to be able to recover improve the string or the data, we need to add the nonce random value to it and then hash. In this way, an intruder can't build up a massive rainbow table because they would have to do this for all of the nonce values that we have. So this will slow down the intruder greatly, even though that we have to store the nonce value along with it. Within common password systems, this is stored in the form of a string with $signs identifying the hashing method. So MD5 is identified with a 1 in OpenSSL, so we have 1, and then we will add the salt, and alongside the salt we'll store the hashed password. So when the user, Bob, logs in, they provide their password. Then the system will take the random salt and add them together. Then take the hash of that, and in this case we should end up with this hash here, and the system will compare with the hash value generated, and if they're the same, then the user can log in. So you can see the problem that we have. If we lose this salt, then it's not going to be possible for us to prove this value unless we go through all the salt values. Okay, so salting is a very important task, and we make sure that we create a random nonce for the salt, and the salt is long enough to make it difficult to compute the hashed value. Along with this, we have the important concept of a collision. And the collision happens when we have two different types of data, but they produce the same hash value. And obviously if it's MD5, it's easier to produce this, and in some programs we can take even an executable program and we can flip bits and produce the same hash, which means an intruder could actually take a valid program and then produce a malicious program that will produce the same hash from there. And it's also been shown that it's possible to take two images. So Matt McHugh took two images, two photographs, and then with a GPU cluster within 10 hours stuffed bytes into each of the images and implemented what's called a birthday attack on this, and eventually produced the same hashed value for the images in there using MD5, which means that you can't really guarantee that the hash that relates to an image cannot be produced by another image, a different image, just because it has a different hash. It cost him 10 cents to run the cluster, and he was able to take two photographs and end up with the same hash value. So this is what's called a collision within our hashing methods. In Windows, there's methods called the LM hash and NTLM, and these were used to store Windows passwords and are often used to breach hash passwords within Windows systems. With OpenSSL, we have a standard method which can check these hash values, and a typical way that we would implement this hashing is with OpenSSL, and then we have the method type, in this case -1. We will then do -salt and enter the salt value, and then at the end we'll add in Fred. So this would be the command we would enter in OpenSSL, and then hopefully what we'll get as a result is this output here. So this is one way that we can actually check our salt value and our password, and then check the hash that we actually have. Another technique that we can use with our hashes is what's called the message authentication code. With this, what we have is that, let's say we have Bob and Alice again. So here is Bob and Alice. At the start of their conversation, they agree a key, a secret key. And this could be negotiated at the start of the session. Then what they do is whenever they have a message, they will take a hash of it and then encrypt it with the key. And this creates what's called an HMAC. So the HMAC is sent with the message, and then because Alice has the same key, she can actually produce the same HMAC. So that proves both that the hash is correct and also that they have the same shared key. Perhaps the key is generated from a password to create this key, and both Bob and Alice have the same password, so they can produce the same HMAC for the data that is transmitted. And in this way, Eve cannot get in between the connection and hijack the session and generate valid HMAC codes. So we typically define these in terms of these methods here, but we define it as HMAC SHA-256, say, and they both agree on that, and they can validate both that they have the same shared key, same shared secret, and also that the data is defined properly with the message authentication code. When it comes to our hashing methods, there is a spectrum. The spectrum relates to the speed of the method, and we go from slow or very slow to very fast. At the top end, fast methods are MD5, SHA-1, and so on. So many of these methods are optimized to run extremely fast. And we might define this as, say, a benchmark of 72 to 134 hashes per second. Obviously, if we run on a GPU, it runs much faster. But just say when we do a benchmark on a system, it gives us about 100,000 hashes per second. The medium speed ones are NT-hash, MySQL, and these ones run around 13k down to 7k, and then we go into the region of the slow hashes, and these are P, B, K, D, F2. This is the hashing method that you would see within Wi-Fi systems, and the reason that Wi-Fi is fairly secure is because we're using a slow hashing method So if we have 8 characters, then it's going to take a long time to compute the secret password which is used to create the hash. So another one that we have in here is Cisco Type 7 method here. And this takes us down to maybe 2,000 to 5,000 hashes per second can be checked on the system. So we went from about over 100,000 down to just 2,000. So this is 50 times faster than that. So if we want to protect our passwords, we would possibly use PPK DFS2 to be able to save them. But we can even make these even slower because they involve a number of rounds. And the more rounds that we set up, the slower it becomes. And then the really slow ones are LM hash, as in the Windows systems, APR1 and bcrypt. And these methods go right down to between 48 and about 700 hashes per second. Again, we can make them even slower, so we can make it run that it's only 1 hash that's checked per second. So when we're protecting passwords, we want to be moving towards this end here to make sure that it's very slow to compute and very costly. And often what happens is that we set up a GPU cluster that might have, say, 4,000 cores in it, and we might multiply that up by 8 of these GPUs, which means that we have 32,000 cores to be able to process these hashes. So we would then multiply up our basic benchmark up by the number of cores that we have. So this can get near gigahashes per second or even terahashes per second. And once we go up towards that region, then we can see that almost every single word from a dictionary could actually be checked against for its hash, even if we have salted the password. So this is generally the way that we need to make sure that we're protected because of these GPUs running very fast from there. Okay, so that's the speed, our MAC addresses, collisions, salts, and the basic methods that we have. Along with this, we can have what's called a one-time password. And with this, we might create what's called a timed hash. So the hash itself might exist for a certain amount of time, and then it will be regenerated after a certain amount of time. So maybe that's every 10 seconds. If every 10 seconds we will rechange the hash, which means that we could have a login system that, given the time, we will only generate the hash for a certain amount of time, and only when the user puts in that hash value will they be able to log in. We can also get other methods that will do that, such as a counter method. So every single time we count, we'll change the hash value, so that each time we log in, we must increment the count and then produce the new hash values. But how do we know the strength of our password or the strength of our hash? For this, we look at key entropy. And with key entropy, we take the log to the base 2 of the total number of phrases that we have that could generate our data. And that's log to the base 10 of the number of phrases divided by log to the base 10 of 2. And that will work out the length of the key length that we have. And that, the longer that key is, the more strength we have. If we used every single password that was possible, and generated every possible hash value, we will get a key entropy of 128 bits. And that's wherever we have a completely random nonce, we will have our key entropy 128 bits, or around that for MD5. But obviously we don't, and what we do is that we take a password and we put it into what's called a key derivation function, and then the output will be a hash value. So really the strength of the hash really relates to the number of passwords that we have. So if I take an example of, say, 1024 passwords, actually that has only got a key entropy of 10 bits in there. Okay, but let's take a real password, and let's say that it has 7 characters. For that, if we go for lowercase, then we can have 26 to the power of 7 different permutations from all A's to all Z's in lowercase. And let's say that we crack at 100 billion hashes per second, then we can compute the total time to compute all of the passwords as 2 to the power of 7 divided by 100 times 10 to the 9 here. And unbelievably, that comes out at 0.08 seconds to take all of the possible lowercase passwords and discover all of the hash values. We could work out the key entropy if we wanted, just by taking 2 to the power of 7 and put it in there and work out what that key entropy is. If we now go for upper and lowercase, 252 to the power of 7 divided by 100 times 10 to the 9, that's 100 billion hashes per second, then we get a better measurement in that it's now 10.3 seconds to crack all of the hash values. So although we might be using a long hash, we'll probably be reducing it greatly. If we tried to all of these hash values, it would take us a long time, even with 100 billion hashes per second. If we wanted to calculate key entropy, it's this value, and then log to the base 10 of that value divided by log to the base 10 of 2, and we should have increased our equivalent key length here. Okay, so this is one way that we would enhance our key entropy from this. So the tool that we often use for this is Hashcat. And Hashcat can read all of these different formats and understands all of the sorting methods that we can get, and does all of these ones here, and it can compute different character sizes for brute force. So with Hashcat, what we do is that we run the command, and then the -m, and then we put the method after that. So 0 is MD5, and then we'll have another value for each of these different methods here. Then we can take our file with a hash in it, and we can output into another file here. Okay, so this command will allow Hashcat to analyze the MD5 method. But we can use different attack modes with the -a option, and one attack mode is to use the dictionary, where we can bring in this is a -a1, and we can bring in a dictionary of common words or common passwords, and then Hashcat will read that in, and then it will perform the brute force on this dictionary. It will take off the salt if there's a salt, and it will add it to each of the words, and tries to crack the hash value. -A3 does what's called a brute force attack, and in this way it will take all of the character sequences and try them out. So in this case it will take all A's to all Z's and try each one from A, and then so on until it gets to the end one. When it finds it, it will stop from there. Okay, so we can see that methods, salting, collisions, MAC, speed, strength, Hashcat, LM, NTLM. One last little thing is that when we use PPK-DFS2, we input a password and we input a salt value, and then out will come a key. That's a common way that we might do this, and some encryption methods will use this. We have a slow, very slow method here. We have our password that we enter. We'll take the salt value stored, and then we could generate a key that would allow us access to a system. Okay, so that's an overview of hashing methods.